Tonight, we're going to follow a star to its worst possible day. I want you to picture a sun like ours. Warm, steady, drifting through space on a quiet orbit around the center of its galaxy. For billions of years, nothing dramatic. Just fusion, light, and a gentle glow into the dark. And then, one day, it wanders a little too close to something it can't see. A black hole, you know the one. The movie version. A dark sphere hanging in space like a cosmic drain. The star gliding in, shrinking, and then just pop, gone. No mess, no drama. Just a neat disappearance and a sad soundtrack. Because here's what nobody tells you. That quiet gulp is a lie. When a black hole eats a star, the universe doesn't dim. It erupts. For a few months, the place around that invisible monster can outshine an entire galaxy. A single doomed star can release as much energy in that brief death scream as our sun will pour out over its entire 10 billion year lifetime. So what actually happens in those last moments? Does the star feel a first, tiny tug of gravity? Like a nudge you barely notice? Does it spiral in politely? Or does it get grabbed, whipped around, and torn apart in a single, catastrophic pass? From the first wobble in its orbit to the instant its light is gone, what's the real, frame-by-frame picture? Here's the paradox. Black holes themselves are invisible. No light escapes the event horizon. And yet, when one of these things shreds a star, telescopes on Earth see a brilliant flare in X-rays, ultraviolet, even visible light. Sometimes we even see jets of matter launched at nearly the speed of light, spearing out of a region that's supposed to be the ultimate one-way trap. How does something that doesn't let light out become one of the brightest beacons in the sky? So, let's start at the very beginning. Tonight we're going to walk through a tidal disruption event like a slow-motion movie. The first subtle stretch as the star crosses the tidal radius. The moment it's pulled into a thin, glowing stream of gas, spaghettified across space. The chaotic swirl as that stream folds back, collides with itself, and settles into a hot, whirling disk around the black hole. Now let's begin to pull that whole sequence apart. How much of the star actually falls in, and how much is flung back out into the galaxy? Where do those jets come from? And what does this violent feeding frenzy tell us about the deeper mystery hiding at the center of all black holes? The information paradox, and whether anything that crosses that final boundary is truly gone. By the end of tonight, you won't just know that a black hole can destroy a star. You'll be able to see every step of that destruction in your mind, from peaceful sun to cosmic noodle to vanishing act. And the next time you hear that a black hole swallowed a star, you'll know it didn't go quietly. So here's the twist. The universe that feels so quiet, so dark and empty most of the time, suddenly screams when a black hole finds a star. We just said that crossing the event horizon is the ultimate vanishing act. No light, no signal, no way back. And yet the moments before that crossing can turn the darkest objects we know into the brightest beacons in the sky. How does something that's literally invisible light up half a galaxy just by eating lunch? Because here's what nobody tells you. The black hole itself doesn't glow. The star does, in its final moments. When a star wanders too close, gravity doesn't politely pull it in. It grabs one side harder than the other, stretching the star into a thin, screaming stream of gas. That tidal disruption is so violent that the energy released in a few months can rival everything our sun will emit over its entire 10 billion year lifetime. Imagine compressing the whole history of the solar system into a season. On human time scales, that is absurd. You live your whole life with the sun just shining. steady, reliable, almost boring. Then somewhere out there, a black hole tears a star apart, and, for a brief moment, that single event can outshine the combined starlight of an entire galaxy. You look up with a telescope, and where there was once a quiet patch of sky, there's a flare so bright it might as well be a cosmic emergency siren. And this isn't just theory scribbled on a chalkboard. Astronomers have watched these tidal disruption events unfold in real time. They've seen flares like ASAS and 14 Alai and AT 2019 QIs surge in X-rays and ultraviolet, then fade over months as the shredded debris falls back, circularizes, and spirals down. We can literally trace the way the light dims, like listening to a death scream echo through space. How often do we get to watch a star die on schedule? Now let's begin to raise the stakes. Every time this happens, the black hole grows. A little more mass, a little more gravity, a little more influence over the orbits of nearby stars and gas. These events don't just make pretty fireworks. They help decide which galaxies feed their central black holes and which ones starve. They can blast gas out of the galactic center, shutting down star formation, or stir and heat the surrounding cloud so new generations of stars are born. So, let's start at the very beginning of the real mystery. If a black hole can reshape its entire host galaxy by devouring a single star, what else is it changing that we haven't seen yet? Does any part of the star truly survive? What actually happens at that final boundary? And how much of this can we ever know from our tiny, flat vantage point in the solar system? In the next section, we're going to follow one doomed star, frame by frame, all the way in. So before we march that doomed star toward the point of no return, let's make a quick deal. If you're still here, if the idea of watching a real star get torn into a glowing stream of gas in slow motion has you leaning a little closer to the screen, you're probably our kind of person. So here's the ask. If you're already hooked, tap subscribe or hit like as a small favor in return. That one click feels tiny from where you sit, but from our side, it's gravity. It pulls in the support we need to keep doing the strange, time-consuming work of turning equations and simulations into a clear, cinematic picture you can actually hold in your head. Because here's what nobody tells you. A tidal disruption event isn't just a cool headline about a black hole eating a star. To explain it properly, we have to build whole visual worlds. How the star orbits through its galaxy, how its path is nudged by other stars, how it slips inside the tidal radius and starts to stretch. That means research, 3D visualizations, and the kind of careful scripting that lets you feel the physics instead of just hearing the words. Your support is what lets us do deep dive episodes on the most extreme events in the universe. Stars shredded into noodles, thousands of kilometers long, black holes that briefly outshine their entire host galaxy, jets of matter screaming out at nearly the speed of light. You know the one, the moment in a documentary where the narrator says, "We watched a star die in real time." We want to slow that down for you, frame by frame, and show what each flash of light actually means. Don't worry, we're not going to drift off into a long channel pitch. This is just a tiny pause at the edge of the abyss. In a few seconds, we're going to rewind the clock on our unlucky star and follow its final approach. The widening tides, the first hints of spaghettification, the instant where the star is still technically whole, but already doomed. No ads for mattresses in between. Just us, the star, and the black hole. And if you stay with us to the end of this journey, you'll walk away with a completely new mental movie of what falling into a black hole actually means. Not a vague cartoon of a dot sliding past a line, but a vivid sequence. The star entering the danger zone. The flare that can outshine a galaxy. The debris whipping into an orbiting disk, half of it flung back into space. So, let's start at the very beginning of the end and watch what really happens as our star crosses the line. And here's where your mental picker quietly lies to you. Because you already think you know what a black hole looks like. You know the one. A perfect dark sphere on a starry background. Or that famous rubber sheet with a deep funnel and a grid. With little glowing marbles spiraling down like water into a drain. Matter goes in, swirls around a couple of times, drops through the cosmic plug hole, and that's it. Curtain down. That image isn't totally wrong. It's just dangerously incomplete. In your head, the story is simple. Cross the event horizon. No escape. Gravity wins. Everything falls toward a point of infinite density. The singularity. End of story. The way we usually tell it, the interesting part happens at that invisible line. And whatever happens on the way in is just background animation. A brief swirl. A fade to black, roll credits. Now let's begin to pull on that thread, because here's what nobody tells you. In the real universe, the event horizon is more like the final page of the book. The plot twist, all the wild physics, all the drama that astronomers actually see happens in the chapters before that page. The familiar textbook funnel makes it look like space is smooth, calm, almost polite as you fall. But the region around a hungry black hole is less like a quiet drain, and more like a roaring, three-dimensional tornado made of fire. Think about how movies usually show it. A star drifts too close. There's a quick zoom, a scream on the soundtrack, and then cut. The next shot is just an empty orbit. The star erased from the picture as if someone deleted a file. No messy middle. No questions about what the star experiences on the way down. It's like a trapdoor in space-time opened under it, and the universe just shrugs and moves on. Pattern interrupt. That trapdoor doesn't slam shut. It explodes first. Because before a star ever touches the event horizon, gravity starts playing favorites. One side of the star feels a stronger pull than the other, and those tidal forces stretch it out into a long, thin stream. Instead of a neat marble circling a drain, you get a glowing ribbon, a cosmic noodle whipping around the black hole. Heat builds, gas collides, light turns brutal. The region that looked like a simple funnel becomes a chaotic, swirling volume of orbiting debris. And yet, something is above the planets. Something is below them. In the same way, there is a hole above and below to that flat funnel diagram you've seen. Real black holes don't just gulp matter straight down. They can fling part of that shredded star back into space, launch jets, and light up their surroundings so brightly they outshine entire galaxies. So the next time you picture a black hole as a clean drain in a flat grid, remember, that's the children's sketch. The real story is messier, hotter, and far more violent, and it all unfolds outside the horizon. Which means, to watch a star truly die in a black hole's grip, we have to stay right there in that dangerous zone and slow the whole thing down. So if we slow that dangerous zone down, frame by frame, something awkward happens to the simple story you've been told. The star doesn't just fall in. It can't. Because here's what nobody tells you. Once a whole sun gets near a black hole, gravity, motion, and tides start arguing over every atom. And that argument takes time. You've seen the usual picture in your head. You know the one. A little glowing ball drifts across a flat grid, reaches the middle, and pops out of existence. Clean, silent, featureless. That picture isn't exactly wrong, but it's dangerously incomplete because it hides the entire middle of the story, the part where the star fights back, loses, and leaves a trail of chaos behind it. A lot of that comes from how we draw this in diagrams and animations. To fit the whole drama into a few seconds, we compress months or years of orbital motion into a single swoop. We skip the awkward in-between phases. The star glides in on a perfect curve, touches the black hole's edge, and boom, cut to black. Your brain quietly learns that infall is instant, that there's no reason to imagine anything interesting happening on the way down. Why would you? The animation never shows it. But now, let's begin to imagine what you'd see if you could watch in slow motion. Not cinematic slow motion. Ridiculous slow motion. As the star approaches, the side closer to the black hole feels a stronger pull than the far side. That difference is the tidal force, the same basic effect that raises ocean tides on Earth, but dialed up until it's homicidal. First, the star bulges. Then it stretches. Its orbit is still trying to carry it past the black hole, while gravity is trying to pin it down, and that tug of war starts dumping orbital energy into heat. Long before anything crosses an event horizon, the star's surface would glow hotter. Its shape would distort into a teardrop, then a noodle. In extreme cases, it's literally spaghettified, drawn out into a long, thin stream of gas, thousands of times its original diameter. And yet, from far away, if you watched in real time, you might still swear it just fell in, because all that violence is crammed into a tiny streak of light. Hidden inside that simple story is a quiet assumption. There's nothing worth talking about between intact star and swallowed star. No real phases, no structure, just a before and an after. That's the assumption we're about to demolish. Because the real nightmare for the star doesn't begin at the event horizon at all. It begins at an invisible boundary farther out, where the black hole's tidal pull finally overpowers the star's own gravity. Astronomers call it the tidal disruption radius. We haven't defined it yet, but once you cross it, there is no safe orbit left, and that's where the real movie starts. So if the real movie starts at that invisible tidal boundary, what exactly are we going to watch tonight? Because here's what nobody tells you. Falling into a black hole isn't one moment. It's a whole sequence of scenes. And once you see them laid out, that simple picture in your head can't survive. So, let's start at the very beginning. We're going to follow one doomed, sun-like star from the safety of its home orbit all the way to its final disappearance. Not as a vague diagram, as a character. We'll give it a path, a black hole to dance with, and a front row seat to its own destruction. Our first question is the big one. How does a perfectly ordinary star ever get close enough to that tidal disruption radius in the first place? Black holes don't go fishing with tractor beams. They sit at the centers of galaxies while gravity and chaos do the work. We'll zoom out to the crowded core of a Milky Way-like galaxy where stars orbit in a thick, tangled swarm instead of a neat solar system plane. And we'll watch how slow nudges, three-body encounters, and disrupted binaries can sling one unlucky star onto a near-miss orbit past the monster in the middle. Once our star is on that fatal trajectory, we zoom in, way in. Now the second question kicks in. What physically happens during the encounter? From the star's own perspective, we'll cross that tidal radius in slow motion. We'll see its near side pulled harder than its far side, its round shape stretched into a teardrop, and then into a long, glowing stream. We'll separate out the stages, capture into a distorted orbit, shredding into a filament of gas, a brilliant flare as debris slams together, the formation of a hot accretion disk, and only then the true swallowing of material past the horizon. Because once you understand that chain, the black hole ate a star stops being a single sentence and becomes a timeline, a process you can replay in your head. Then we pull the camera back out past the event horizon, past the swirling disk, all the way to us. That's our third question. What can we actually see from Earth? We'll stand next to real telescopes that have caught these tidal disruption events. Watch how a galaxy suddenly brightens in X-rays and ultraviolet, and learn how astronomers read that fading light curve like an autopsy report for a star. And yet, something is above the planets. Something is below them. In the same way, there's a before and after to the star's information that doesn't line up neatly with the black hole's clean edge. Along the way, we'll have to confront time dilation, the information paradox, and the eerie question of whether any trace of our star's story survives beyond the horizon. Now let's begin the fall. By asking a deceptively simple question. Where does this actually happen? Because black holes aren't out there randomly snacking on stars in empty space. These encounters have a favorite stage, and it's one of the most extreme neighborhoods in the universe. So, let's start at the very beginning. Take a galaxy, like our Milky Way. At its center, buried under layers of dust and stars, sits a supermassive black hole. You know the one. In our case, it's called Sagittarius A, about 4 million times the mass of the Sun, crammed into a region smaller than Mercury's orbit. It's quiet most of the time, but it's surrounded by exactly the kind of crowd that can feed it. Near the heart of a galaxy, the picture stops looking like our tidy solar system diagram. There is no simple, flat plane with everyone politely spaced out. Instead, you get a three-dimensional swarm. Stars of all sizes race around the center on elongated, tilted, intersecting paths. Some whip around in just a few years. Others loop out and back over centuries. It's less like a calm planetary system, and more like a gravitational mosh pit. Because here's what nobody tells you. Most stars never see any of this. They spend their entire lives cruising in the galactic suburbs, tens of thousands of light years from the central black hole, where its pull is just part of the general background gravity. From there, the monster in the middle might as well be a rumor. So how does a perfectly ordinary star end up on a death plunge? Very slowly. Over millions to billions of years, tiny gravitational nudges from passing stars, from dense clusters, from giant molecular clouds, all add up. Each close pass tilts the orbit a little, stretches it a little, shifts its orientation around the galactic center. One nudge does nothing. 10 million nudges can redirect a life. In the crowded central parsec, these long-term tugs can push a star onto a path that dives much closer to the supermassive black hole than it ever went before. Most of those stars still miss, slingshotting around and back out. But every so often, one gets steered onto a trajectory that threads directly through the danger zone where tidal forces can shred it. Smaller, stellar mass black holes can also play this game. In dense star clusters, a 10 solar mass black hole can rip apart a passing sun-like star, creating a brief, violent flare. Those events are real, but from our vantage point they're harder to spot, dimmer, and shorter-lived. The big cinematic tidal disruption events we actually catch across hundreds of millions of light years almost always involve supermassive black holes in galactic centers. And yet something is above the planets, something is below them. In the same way, above and below the calm disk of a galaxy, there's this chaotic core, constantly reshuffling stellar orbits. Before a star can be spaghettified, it has to be delivered into a dangerously close orbit first. In the next part, we'll unpack how those slow, invisible gravitational games finally tip a single unlucky star over the edge. So picture that calm galactic disk again, with its neat spiral arms and glowing lanes of gas. Hidden inside that picture is a region that behaves less like a clockwork model and more like an arcade game. A very slow arcade game. Around a supermassive black hole, the stars are packed so tightly that their gravity keeps nudging each other, like pinballs tapping the bumpers over and over. Now, let's begin with those nudges. In a dense nuclear star cluster, no star follows a perfectly smooth, eternal orbit. Every close pass with a neighbor gives it a tiny gravitational kick. Too small to notice in a year, huge over 1 billion years. One encounter tilts the orbit a little above the galactic plane, another drags it below, another stretches it into a long ellipse that dives closer to the center. Because here's what nobody tells you. Chaos in space doesn't look like explosions. It looks like a slow drift in orbital parameters. Astronomers have a very unromantic name for this: two-body relaxation. Each pair of stars briefly forms a little two-body system, trades momentum, and then moves on. Most of the time, these are small course corrections, but sometimes a third player barges in. In a three-body encounter, especially with a binary star, the game changes completely. You know the one. Two stars orbiting each other, minding their own business, until the black hole's gravity and a passing star crash the party. In that moment, the binary can be ripped apart. One star gets flung outward at incredible speed, kicked onto a wide, safe orbit, or even ejected from the galaxy as a hypervelocity star. The other star loses energy and ends up bound more tightly to the black hole, dropped onto a much more plunging path. It's like the cosmic pinball machine just rang up a jackpot and sent one ball screaming off the table while the other heads straight down the middle toward the drain. Over millions to billions of years, this slow-motion pinball reshuffles the entire nuclear cluster. Most stars just wander to slightly different paths. A tiny fraction, though, gets shoved onto nearly radial orbits that dive almost straight towards the black hole. That's the dangerous population. Those orbits thread a special region of phase space that dynamicists ominously call the loss cone. The loss cone is the set of orbits that pass so close that a star will be swallowed or tidally disrupted. Once a star falls into that cone, it doesn't hang around. It either disappears behind the event horizon or gets shredded, which means those orbits are constantly being depleted and slowly refilled by new gravitational kicks. And yet, something is above the planets. Something is below them. In the same way, above and below the average safe orbit in a galactic core, there's this thin, invisible cone of doom. Once a star slips into it, its fate comes down to a brutally simple competition. Can its own gravity hold it together, or will the black hole's tidal pull rip it apart first? In the next part, we'll follow one doomed star as it crosses that line. So now we need to draw two invisible lines around this black hole, because here's what nobody tells you. When a black hole eats a star, there isn't just one critical boundary. There are two. And which one the star crosses first decides whether the universe gets a show or total silence. The first line is the tidal disruption radius. That's the distance where the black hole's gravity doesn't just pull on the star as a whole, It pulls noticeably harder on the near side than the far side. The star's own self-gravity is trying to hold it together. The black hole's tidal gravity is trying to pull it apart. At the tidal disruption radius, that tug of war breaks in favor of the black hole, and the star loses. The second line is the celebrity you already know, the event horizon. You know the one, the point of no return. Cross that, and not even light can climb back out. It's not where you get torn apart, it's where the outside universe loses the ability to see what happens next. One line decides if the star survives as a star. The other line decides if the rest of us get to watch. So, let's start at the very beginning of this deadly geometry. For a relatively modest supermassive black hole, say a few million times the mass of the Sun, the tidal disruption radius actually lies outside the event horizon. That means a star gets shredded while it's still in view of the cosmos. Its gas is pulled into a long, glowing stream. It heats up, and for a few months, that flare can outshine the entire galaxy around it. Astronomers have seen this in real time, watching a quiet galactic core suddenly blaze in X-rays and ultraviolet light. But crank up the black hole's mass to hundreds of millions or billions of suns, and the picture flips. The event horizon swells faster than the tidal radius grows. Now the tidal disruption radius can end up inside the horizon. What does that mean for a wandering star? It crosses the event horizon still mostly intact, still a star in its own frame of reference, and then it's torn apart in the dark, hidden from us. No bright flare, no dramatic debris arc, just a silent disappearance. From the outside, the universe barely shrugs. Our doomed star? Its orbit threads the needle. It will skim just inside the tidal disruption radius, but still outside the event horizon. That's the worst possible place to be. In the next part, we'll watch what happens when a whole sun's worth of gas is forced to choose, spiral into the black hole, or explode across space first. Our doomed star has made its choice. It's crossing the invisible line where orbiting a black hole turns into being remade by it. And the first thing that changes isn't brightness or color, it's shape. Now let's begin with the force that does the sculpting. Gravity. But not just how hard you're pulled. What matters here is how uneven that pull is from one side of the star to the other. The side closer to the black hole feels a stronger tug than the far side, so the star isn't falling as one solid unit. It's being argued over, piece by piece. You've seen a gentler version of this at home. Earth's oceans rise and fall in tides because the side facing the moon is pulled a little harder than the far side. Same gravity, different distance, different pull. Because here's what nobody tells you. Tides are just gravity disagreeing with itself across an object. Now scale that calm ocean picture up until the ocean is an entire sun. Our star is racing along its orbit, but the black hole's tidal forces are so intense that they start to reshape the whole star into a long, thin form. Not a neat ball of fire anymore. More like a glowing, cosmic noodle trying to wrap itself around an invisible drain in space. At first, the distortion is subtle. The star bulges slightly along the line, pointing towards the black hole and away from it, turning from a sphere into a kind of squashed ellipsoid. If you could pause the scene here, it would still look like a star, just a bit stretched, like someone gently pulling on a rubber ball. But the closer it dives toward that tidal disruption radius, the more dramatic the change becomes. Here's the pattern interrupt. The star is not helpless. Inside, its own pressure and internal gravity are fighting back. The hot gas wants to spring outward. The The star's self-gravity wants to pull everything back into a sphere, and the black hole's tidal field is trying to tear that symmetry apart. Which side wins? For a while, it's a tense draw. As the star swings through its final approach, the tidal forces ramp up much faster than the star can respond. The near side races ahead, the far side lags behind, and the once-round star is dragged out along its orbital path into a dramatic, elongated shape. It's still technically one object, but only barely. You can think of it as a star in denial, stretched into a luminous strand that refuses to admit it's already becoming debris. And yet, something is above the planets. Something is below them. Here, something similar is happening along the star. Regions closer in are doomed. Regions farther out are almost safe. There's a critical moment coming when that internal balance finally snaps, and the star stops being a single, coherent body at all. On one side of that moment, you have a tortured star. On the other, you have a river of gas. In the next section, we'll slow that transition down and watch the instant a sun turns into a stream. So let's cross that line in slow motion. One moment, you still have a horribly distorted but recognizably whole star. A heartbeat later in orbital time, you don't. You have something new, a stellar body that has forgotten how to be a sphere. The key is where the star passes relative to the black hole, inside the tidal disruption radius. That's the distance where the black hole's tidal pull isn't just stronger than the star's surface gravity at one point. It's stronger everywhere. Because here's what nobody tells you. Once every layer of the star feels tides that beat its own gravity, there is no core that can hold the rest together. The star's self-gravity loses the tug-of-war at every depth. Cohesion stops being an option. Material begins to peel off. Not in a cinematic fireball, but like a cosmic taffy pull. The leading side of the star, closer to the black hole, is yanked ahead along the orbit. The trailing side lags behind, still trying to go where the star used to be. In between, the body is stretched, thinned, and drawn out until that once-round star becomes a long, narrow stream of gas threading past the black hole. You know the one. In every artist's impression, it looks like a glowing ribbon looping around a dark center. This isn't an instant explosion. It's fast, but it's orbital fast. Over a fraction of a single swing around the black hole, the star is converted from sphere to stream. Depending on the exact path and on how dense the star is, you can get different outcomes. A grazing pass might only strip the outer layers, leaving a battered core to escape and orbit the galaxy again. A deeper plunge means full tidal disruption. Nothing solid survives, just that elongated river of plasma tracing the original orbit. Along this new river, not every parcel of gas shares the same fate. The tidal forces don't just stretch, they also redistribute energy. Some chunks of the stream lose orbital energy and become tightly bound to the black hole, destined to loop back and, later, help build a brilliant accretion disk. Other chunks gain energy, get flung onto escape trajectories, and are hurled back into interstellar space at thousands of kilometers per second. In a sense, the black hole uses the star to throw part of the star away. So here's the twist. Only about half of the star's mass actually ends up feeding the black hole. The rest is exiled. Where does that escape material go? How does it reshape the space around the black hole? And how can we, from our little flat solar system plane, possibly know any of this is happening at all? In the next section, we'll follow the returning stream and watch it light up the darkness. So here's the weird part. A star can be torn in half by a black hole, and the universe just lets one half walk away. The other half is sentenced to the deepest gravity, well in space. Simulations and real tidal disruption events back this up. Roughly 50% of the shredded star ends up gravitationally bound to the black hole, while the other 50% is unbound and escapes. That's not a poetic split. It literally comes from how the star crosses the point of closest approach, with some gas gaining energy and some losing it. Because here's what nobody tells you. A tidal disruption isn't a simple in or out decision. It's a violent sorting machine. Let's follow the escapees first. The unbound debris is flung outward on hyperbolic trajectories, moving too fast ever to fall back. Imagine a long, thinning spray of stellar gas racing away at thousands of kilometers per second, carving through the surrounding galactic environment. This isn't just a dramatic exit. As that material plows into the ambient medium, it seeds it with freshly processed elements from the star's core. In a sense, every black hole meal throws a chemical flare into its host galaxy, enriching the space around the center the way supernovae enrich the flat disk of our own solar system. And yet, something is above the planets. Something is below them. In the same way, something is bound to the black hole, and something is free. The bound half of the star doesn't just spiral straight in like water down a drain. It follows extremely elongated, almost comet-like orbits, stretched out into a thin stream that swings far out and then dives back toward the black hole. So, let's start at the very beginning of that return journey. Each loop takes time. Each pass converts orbital energy into heat and radiation. The result is a delayed feeding process, not an instant gulp. Now, let's begin to talk about what we actually see from our little flat solar system plane. As the bound debris falls back, the rate at which it returns to pericenter typically follows a characteristic power law decay. In simple terms, there's an early peak in the fallback rate, then a steady fade that often tracks something close to 1 over time to the 5/3. It sounds abstract, but this mathematical curve is written directly into the light. The tidal disruption flare brightens and then dims along that same pattern. By measuring how quickly the flare fades, how smooth or jagged that decline is, astronomers can back out the original mass of the star, the mass of the black hole doing the shredding, and even the geometry of the encounter. Was the orbit nearly parabolic? How deep did the star plunge? Did the debris stream collide with itself efficiently and form a disk, or did it take the scenic route? Those details change the light curve, because once you realize that half a star escapes and half returns on a schedule, you see why these events are more like cosmic time-release capsules than single explosions. In the next section, we'll watch that bound stream collide with itself, circularize, and ignite an accretion disk that can briefly outshine an entire galaxy. So now you've got this elegant mental picture. Half a star flung away, half returning on cue. But when that bound material comes back, it doesn't just dive straight into the black hole like water down a drain. It does something much stranger. Because here's what nobody tells you. The first act of feeding a black hole is messy, chaotic, three-dimensional in a way our neat diagrams almost never show. Each packet of gas returns on a long, stretched out, highly eccentric orbit. You can think of it like a broken solar system where every planet is a fragment of the star, racing on a skinny ellipse that skims close to the black hole and then shoots far back out into space. And thanks to general relativity, those ellipses don't close. The point of closest approach precesses. So when the stream swings back around, it doesn't retrace its own path. It misses, just enough. That tiny mismatch is everything. Because when one loop of the stream comes back in, it slams into another loop that's already trying to leave. Self-intersection. Head-on collision. The result is a series of violent shocks that turn orderly orbital energy into heat and turbulence. So instead of a single thin ribbon, you start getting a puffy, tangled cloud of gas, trying to find a new, more circular orbit around the black hole. Now let's begin to turn that chaos into an engine. Every shock robs the gas of a little orbital energy, an angular momentum. Over many passes, those eccentric paths shrink and round off. The stream thickens, spreads, and settles into a roughly circular configuration, an accretion disk. Not a calm, flat record like the solar system in a textbook, but a hot, swollen torus of plasma, glowing in X-rays and ultraviolet light. You know the one. The classic sci-fi picture of a black hole with a bright ring. This is the real physical origin of that image. Inside this disk, gravity is doing brutal work. Gas closer in orbits faster than gas farther out, so layers rub against each other, creating friction, magnetic turbulence, and more shocks. Gravitational potential energy is relentlessly converted into heat and then into radiation. For a brief time, a single black hole plus its freshly formed disk can outshine an entire galaxy, releasing in months what our sun will emit over billions of years. But there's a catch. The disk doesn't always ignite instantly. In some tidal disruption events, the optical flare from the first shocks appears early, while the X-ray emission from the inner disk turns on only after weeks or months. The returning stream has to collide, circularize, and thicken before the innermost regions get hot enough to blaze in high-energy light. So once this churning disk is in place, what happens next? How does gas actually spiral inward across that final, fatal stretch of orbit? And why does that slow fall light up the cosmos so dramatically that we can see it from hundreds of millions of light years away? In the next sections, we'll zoom in on the disk itself and watch the black hole finally start to eat. Here's the twist. When the black hole finally starts to eat, the universe doesn't go dark. It flares violently. The star's death doesn't look like a light being switched off. It looks like a lighthouse suddenly turned up to maximum, screaming across space. Because here's what nobody tells you. The real action isn't at the event horizon. It's in the crowded, chaotic traffic jam of gas just outside it, in the accretion disk we've been building up. That disk is where gravity does its most spectacular work, turning a quiet fall into a cosmic power plant. So, let's start at the very beginning of that final plunge. The stellar debris doesn't drop straight in. It orbits. It circles in a flattened plane around the black hole like a distorted, furious version of the solar system. To move inward, that gas has to lose angular momentum, passing it outward through friction, turbulence, and magnetic fields. Every tiny jostle in that disk is gravity stealing a little more order and turning it into heat. As the gas spirals closer, it falls deeper into the gravitational well, trading altitude in that invisible landscape of space for speed. Where does the lost gravitational potential energy go? It gets shredded into heat as neighboring rings of gas rub past each other at thousands of kilometers per second. The inner regions become a maelstrom so hot that ordinary atoms can't stay intact. By the time the gas reaches the innermost orbits, It's no gentle glow. It's superheated plasma, tens of millions of degrees, blasting out ultraviolet and X-ray radiation. That's the paradox. An object defined by darkness is surrounded by a disk that can outshine entire galaxies in high-energy light. You know the one, the classic artist's picture of a black hole with a bright, glowing ring? That's not artistic license. That's accretion physics doing its job. Here's the wild comparison. Nuclear fusion in stars, the process powering the sun, converts about 0.7% of the fuel's mass into energy. Black hole accretion can convert 10 times that, even up to around 40% in extreme cases. Per kilogram of gas, a hungry black hole can be one of the most efficient engines in the universe. How do you compete with something that turns falling into pure light? During a tidal disruption event, when a single star is shredded and fed to the disk, that efficiency goes on full display. For a few weeks or months, the accretion-powered flare can rival the output of an entire galaxy of hundreds of billions of stars. Astronomers have watched these flares fade in real time, like a slow-motion cosmic scream. And yet, something is above the planets. Something is below them. Just like our solar system's flat diagrams hide a three-dimensional reality, these blinding flares are only one layer of the black hole's meal. In the next section, we'll follow what escapes: the winds, the jets, and the debris blown back into space instead of being swallowed. So those flares are the first layer. The black holes burp, but sometimes the meal gets weaponized. In a few tidal disruption events, the chaos around the black hole doesn't just glow, it fires. From near the poles, the system launches razor-thin jets of particles and radiation that slice through space like a cosmic laser. Imagine a quiet galaxy minding its own business, and then, for a few weeks or months, one spot in its core turns into a lighthouse you can see across the universe. These aren't gentle beams. They're made of plasma and high-energy photons, blasting outward at a large fraction of the speed of light. Because the material is moving so fast, relativity starts to matter in a very literal way. Time appears to slow for the jet material. Light gets beamed forward into a narrow cone. And to us, if we happen to sit in that cone, the whole thing looks absurdly bright. A galaxy that was a faint smudge yesterday can suddenly outshine everything else in the picture. Because here's what nobody tells you. When a jet points almost exactly at us, that once dormant black hole can masquerade as a blazar, the same class of monster we usually associate with actively feeding supermassive black holes that have been gorging for millions of years. Only this blazar-like phase is temporary, powered by a single unlucky star that wandered too close. It's like turning on a quasar with one meal. One of the clearest examples is an event called Swift J1644+7. Back in 2011, a NASA satellite designed to catch gamma-ray bursts saw something strange. An intense, flickering X-ray source that wouldn't fade the way a normal explosion should. The brightness changed on timescales of minutes, telling us the emitting region had to be tiny, just light minutes across, near a central black hole. The best explanation? A relativistic jet launched from a newborn accretion flow, powered by the remains of a shredded star. But how do you actually make a jet like that? So, let's start at the very beginning of the engine. As the stellar debris settles into a spinning disk, it drags magnetic fields along for the ride. Those fields thread the disk and the black hole itself, twisting into helical structures that can grab hold of charged particles and fling them outward along the rotation axis. In leading models, the disk's turbulence amplifies the fields, while the black hole's spin donates energy. This is where the Blandford-Znajek mechanism comes in. In that picture, magnetic field lines anchored in the disk tap into the black hole's rotation, extracting its rotational energy and channeling it into the jets. In a sense, the black hole becomes an enormous electromagnetic generator, turning gravity and spin into focused beams. And yet, something is above the planets. Something is below them, just like a flat solar system diagram hides the true three-dimensional orbits. These brief blinding jets hide a deeper question. From our tiny vantage point, catching only flashes of X-rays, radio waves, and fading optical light, how do we reconstruct the entire sequence of violence? The shredding, the disk, the jets, using nothing but those fleeting signals. Now, let's begin to reverse engineer the crime scene. We don't just see a black hole eat a star. We catch the echo, the death scream. And we do it from hundreds of millions of light years away, using a trick that sounds almost too simple. We watch the whole sky over and over and wait for something to flare where nothing was before. So, let's start at the very beginning of that process. Wide field surveys like ASS, SN, ZTF, and PAN-STARRS sweep huge chunks of space every clear night, taking rapid-fire images of the same galaxies you'd barely notice in a backyard telescope. Software compares tonight's picture to last week's, pixel by pixel. If a new point of light suddenly appears, brightens, and then starts to fade over weeks to months, alarms go off. Because here's what nobody tells you. The universe is mostly quiet on human timescales, so anything that changes fast is shouting. Most of those shouts are supernovae, exploding stars out in the disks of galaxies. But tidal disruption events hide in a different place. They pop up right in the nucleus, in the tiny central region where the supermassive black hole lives. Astronomers call them nuclear transients, and that location is the first clue. The second clue is the way they fade. A supernova flares and declines in a fairly standard pattern. A TDE's light curve often follows a slower, power law drop as the shredded debris falls back in. Same basic picture on a chart, totally different crime. You know the one tool that makes this work even better? We don't just look in visible light. As soon as a candidate TDE appears, telescopes pivot across the spectrum. Optical and ultraviolet to watch the hot gas glow. X-ray observatories to see the inner accretion disks light up. And radio arrays to catch any jets or outflows plowing into surrounding gas. In X-rays, you're practically staring at the innermost orbits. In radio, you're tracking shock waves racing through intergalactic space. When ASA SSN 14 Li went off in 2014, surveys caught it early, right as the flare was rising. Follow-up telescopes watched for months as the X-rays brightened, softened, and faded, tracing the debris stream as it circularized into a disk. A 2019 KAIS was even more of a gift, spotted so quickly that we saw the star's atmosphere being blown off in real time, then watched the outflow slow and cool. For a brief moment, we had a front row seat to a black hole building its dinner plate. And yet, something is above the planets. Something is below them. In the same way, each new tidal disruption sits above or below our expectations. A fresh experiment run by gravity itself changed the star's mass, the black hole's size, the exact orbit, and the whole light show shifts. By stacking these events, one by one, we're slowly turning a handful of eerie flashes into a working theory of how black holes feed. But there's still one question those light curves can't answer directly. What happens to the matter that doesn't fall in? To answer that, we need a star that died loudly enough, for us to watch the whole sequence unfold, not just a flash on a graph, a full-on, slow-motion shredding. Now let's begin with one of the clearest cases we've ever seen, an event called Accretion 14 You know the one. Or at least, you've seen its fingerprints in headlines about a star being eaten by a black hole. Accretion 14 showed up in 2014, about 290 million light-years away, flagged by the All-Sky Automated Survey for Supernovae. This network is basically a robotic patrol of the night sky, scanning for anything that suddenly brightens, except this flare didn't look like a normal supernova. Its light rose, then faded in a way that made theorists sit up and go, "Hang on, we've seen that curve on paper." Because here's what nobody tells you. When a star is torn apart, the real drama is in how the light changes with time. As the stellar debris falls back toward the black hole, theory predicts a very specific pattern. The feeding rate should spike, then slowly decline, following a mathematical power law as the new accretion disk settles. Accretion 14 did exactly that. Over months, its brightness climbed, then faded in a smooth, predictable arc, like a cosmic bell ringing and slowly going quiet. The light curve was not just pretty. It was a checklist of tidal disruption physics being ticked off in real time. But the real prize came when astronomers turned more than one kind of telescope on it. X-ray observatories locked onto a searing hot inner region, the newborn accretion disk glowing at millions of degrees. Radio telescopes, on the other hand, picked up emission from material being pushed outward, a slower, cooler echo of the violence near the event horizon. In one object, we could see both the feeding and the burping of the black hole, and test our models of how disks form, how winds launch, and how gravity sculpts the flow of matter in extreme space. So how fast was that gas really moving? That's where the spectrum came in. When you split the light from Accretion 14 Li into its component colors, you get sharp spectral lines from specific elements in the torn-up star. Those lines were broadened and shifted by Doppler effects, telling us the gas wasn't just drifting. It was racing around at significant fractions of the speed of light near the black hole's gravitational well. You could read its orbit, its speed, even its changing temperature, straight from those tiny wiggles. Put all of this together, and Accretion 14 becomes more than a headline. It's a textbook demonstration that the sequence we've been walking through, star shredded, debris flung out, material falling back, disk igniting, outflows roaring away, isn't a thought experiment. We've watched it play out, frame by frame, in real data. And yet something is above the planets. Something is below them. The same way our flat solar system picture hides a three-dimensional reality. These light curves hint that there's still one more layer to how black holes feed that we haven't unpacked yet. So what does Accretion 14 still leave unexplained? And what happens when the black hole doesn't just sip, but launches something back at the galaxy? Accretion 14 was the quiet, steady meal. A2019 QIs was the black hole's messy dinner party, caught from the very first spill. Astronomers call it a Rosetta Stone tidal disruption event, because here's what nobody tells you. Usually, by the time we notice a black hole shredding a star, the main fireworks have already gone off. With AT2019 QIs, we caught the match striking. We saw the flare rise, not just the fading embers, so let's start at the very beginning of this one. In late 2019, automated surveys flagged a new point of light in a nearby galaxy. At first glance, it looked like a normal supernova. Bright, sudden, explosive. But when telescopes swung over and started taking spectra, the fingerprints didn't match a dying star blowing itself apart. They matched a star being torn apart by gravity. Early on, optical and ultraviolet telescopes watched the flare climb in real time. Day by day, you could track the rise as fresh debris from the disrupted star fell back toward the black hole, heating up and glowing hotter and bluer. It's like seeing the dimmer switch on a galactic spotlight being cranked up, instead of only catching it halfway. Then the rest of the spectrum joined the party. As weeks turned into months, X-ray observatories started to pick up high-energy photons sneaking out through the chaos. Radio telescopes, tuned to much longer wavelengths, detected a growing signal too. That combination told us something crucial. The black hole wasn't just swallowing, it was launching. A 2019 QIZs showed clear signatures of gas being blown away from the center at thousands of kilometers per second. Not some gentle breeze, but a fast, dense outflow. Radiation pressure from the flare and winds from the forming accretion disk were literally shoving part of the star back into space. Half the sun's worth of material in, a huge fraction blasted out. Now let's begin to twist the picture. Those outflows didn't just escape, they obscured. Modeling the light curves and spectra suggested that a thick, clumpy shroud of gas wrapped around the black hole, intercepting the raw, inner disk emission and re-radiating it at cooler wavelengths. So some of that early optical and UV light, it wasn't the naked accretion disk at all. It was reprocessed glow from a surrounding cloud, a kind of cosmic lampshade hiding the brightest bulb. Because once you understand that geometry, you realize how easily a flat, simple flare can fool us. Change the angle of our orbit around the event, tilt that gas plane just a little, and the whole show looks different from Earth. And yet, something is above the planets. Something is below them. In the same way, something is hidden, above and below this tidal debris plane, vanishing past the event horizon. If we can now watch a star's death in such detail outside the horizon, can we finally start to ask what happens to its information and structure once it crosses the point of no return? To answer that, we have to do something strange. We have to stop watching from far away and, just for a moment, fall in with the star. From the outside you see drama, a bright flare, a shredded arc of gas, light slowing and fading near the event horizon. But from the star's own point of view, there is no single cinematic impact with a sharp edge in space. There's no glowing wall to hit. There's only a steady pull that becomes unbearable, because here's what nobody tells you. The real violence starts long before the horizon. As the star dives in, gravity doesn't pull on every part of it equally. The side closer to the black hole feels a stronger tug than the far side. That difference in pull is the tidal force, and it stretches the star along its orbit. First, it just distorts, like a slightly squashed sphere. Then it lengthens into a cigar, then into a noodle. You know the one, the infamous spaghettification picture. By the time the remains approach the event horizon, the original star is less a single object and more a flowing cloud of gas. Now let's begin to think in relativity's language. In general relativity, what matters for the falling star is its own proper time, the time on a clock riding along with the gas. In that frame, the gas crosses the event horizon in a perfectly finite time, seconds to hours, depending on the scale. There is no local signpost saying, "You have arrived at the horizon." No sudden jolt, no wall, no change in the laws of physics right at that invisible plane. So why does every diagram make it look like the plunge freezes at the edge? Because from our distant vantage point, clocks near the horizon appear to slow down. Light climbing out loses energy, its color stretched to red, then to radio, then effectively to silence. To us, the infalling stream seems to hover and fade at the horizon, never quite crossing. Two perspectives, one reality. Here's the twist that really breaks the flat, tidy picture in your head. For a disrupted star, most of its material never reaches the horizon as a coherent ball at all. It's already been torn into a long stream, heated to millions of degrees, some of it whipped into an orbiting disk that lights up the surrounding space. Only part of that gas spirals inward. Another large fraction is flung back out into the galaxy. So, let's start at the very beginning of your intuition and rewrite it. There is no single, final instant where the intact star hits the horizon and blinks out. There's a gradual disassembly, a slow unweaving of structure, and then different parcels of gas crossing that one-way boundary at different times in their own clocks. And yet, something is above the planets. Something is below them. In the same way, something remains outside, still radiating, even as other pieces vanish beyond return. Which leaves one last, unsettling question. If nothing special happens at the horizon for the falling gas, where and how does the information about that star really disappear? So here's the twist. For all this talk of swallowing a star, a close pass by a black hole doesn't always end in total obliteration. Sometimes the star limps away, scarred, lighter, but still very much there. Because here's what nobody tells you. Tidal encounters come in degrees. If a star just grazes the danger zone, the black hole's gravity can strip off only its outer layers, like peeling the atmosphere and puffy envelope away, while a dense core survives and slingshots onto a new orbit. To a distant observer, you see a flare, a bright scream in X-rays and ultraviolet. To the star, it's more like a brutal crash diet. Now let's begin to picture that orbit. The survivor doesn't just go back to its old quiet life. It's now on a stretched, elongated path that can bring it back around for another close pass. And another. Each time the black hole reaches out with those tidal claws and peels away more mass. You can imagine a once sun-like star gradually stripped down to a hot helium-rich core, or something that looks a lot like a low-mass white dwarf, forged not in a gentle stellar wind, but in repeated near-death encounters. So, let's start at the very beginning of what decides its fate. Simulations show a whole menu of outcomes depending on details you never see in the simple textbook picture. How centrally concentrated the star is, whether it's a puffy giant or a compact dwarf, the exact angle of approach, and how close the closest approach actually is compared with the tidal disruption radius. Skim just outside that radius and you'd get a partial disruption. Dive deeper, and the star is shredded completely into a long, thin stream of gas. We know this isn't just theory because the sky has started to cooperate. Some tidal disruption events flare much less brightly than a full stellar meal should. The light curve fades too fast, or the total radiated energy suggests only a fraction of a solar mass was actually fed to the black hole. In a few galaxies, we've even seen repeated flares from the same nucleus over years, as if the same unlucky star is being nibbled at on each orbit rather than swallowed in one gulp. Cosmic fast food, not a sit-down dinner. And yet something is above the planets. Something is below them. In the same way, something remains after these encounters that doesn't quite fit our neat categories. Could some of the odd, compact objects we see near galactic centers today be survivors of ancient, near-fatal brushes with supermassive black holes, stripped cores silently circling the monster that almost unmade them? And if so, what secrets about gravity, matter, and information are locked inside those half-destroyed stars, still orbiting just outside the point of no return? Those half-destroyed stars raise a bigger, stranger problem, because if a black hole can almost unmake a star, we have to ask, what exactly gets unmade? What really disappears when gravity wins? Now let's begin with a famous headache at the center of all this: the black hole information and paradox. In quantum mechanics, information about a system's exact state is sacred. You can scramble it, you can hide it, but you can't truly erase it. Classical black hole physics, on the other hand, gives you a brutally simple picture. Once something crosses the event horizon, only three numbers matter from the outside: mass, charge, and spin. Everything else? Gone from the visible universe. So which picture is lying to you? You know the one. The neat diagram where matter falls in, horizon closes, end of story. Because here's what nobody tells you. When a star is torn apart in a tidal disruption event, we don't just see it fall into darkness. We can actually follow its information as it's carved up and flung around. The star's mass, its chemical composition, its angular momentum, those aren't abstract ideas. They shape the flare we see. About half the star's material is hurled back into space, and that outflow carries a very real fingerprint of what the star was made of. The rest spirals inward, forming that hot, bright accretion disk and, in some cases, pencil-thin jets screaming out at nearly light speed. Those X-ray and ultraviolet flashes, those radio jets, are not just fireworks. They're the visible trace of how the star's properties and the black hole's gravity negotiate a truce. But here's the catch. The radiation we detect is messy. It's thermal, turbulent, smeared out over time. You can't simply rewind the flare and reconstruct the star atom by atom. The information is encoded, yes, but in an almost absurdly scrambled way. It's like trying to reconstruct a library from the spectrum of the fire that burned it. And deeper down, past the glowing disk and the jets, the real paradox waits. Does the fine-grained quantum information about every particle in that star survive, hidden in the black hole's microscopic degrees of freedom, or leaking out over eons in Hawking radiation? Or is some part of reality truly lost at the horizon? Right now, no theory has a fully satisfying, tested answer. What tidal disruptions do give us is a laboratory, not a clean, controlled solar system lab on a flat table, but a wild, high-energy arena where we can test black hole thermodynamics, accretion physics, and how information flows in extreme gravity. And yet something is above the planets. Something is below them. In the same way, there's what we can see blazing outside the horizon, and what might be hiding just beyond our reach. In the next part, we'll push even closer to that edge and ask what happens to time, light, and cause and effect as you cross the point of no return. So if there's a visible side and a hidden side to these encounters, the next question is brutal and simple. How big does a black hole have to be to actually eat a sun? Not just nibble at it. Swallow it. Now, let's begin with two competing radii that decide the whole drama. One is the event horizon, the point of no return. The other is the tidal radius, where gravity's difference between the near side and far side of the star becomes so extreme that the star is pulled apart. If the tidal radius sits outside the horizon, the star dies loudly, If it's inside, the star dies in silence. Because here's what nobody tells you. There is a sweet spot. For a sun-like star, you want a black hole that's roughly between 1 million and 100 million solar masses. In that range, the tidal radius lies safely outside the event horizon. The star gets shredded before it crosses the edge. Its gas whipped into a glowing stream, an accretion disk, maybe even jets that can outshine an entire galaxy for a few months. That's when we see those spectacular tidal disruption events lighting up distant galactic centers. But what if the black hole is smaller, say a few 100,000 suns, or less? Then the tidal radius is still outside the horizon. The physics of spaghettification still happens in the open. But the whole show is closer in, more compact, and often less efficient at turning gravity into light. The flare can be fainter, shorter, easier to miss against the background glow of a busy galaxy. From our vantage point, those meals are happening, but they're whispering rather than screaming. Push the mass up instead, to the real monsters. Hundreds of millions, billions of solar masses. Now the geometry flips. The event horizon balloons, outward faster than the tidal radius. A sun-like star can cross the horizon intact, only to be torn apart in the dark, with almost no light escaping to announce what just happened. It's a dark capture. The black hole grows. The universe barely notices. So across the cosmos, some galactic centers may be quietly swallowing stars invisibly, while others flare like cosmic flashbulbs every time a star strays too close. Same basic process. Very different picture on our telescopes, all because of mass. So, let's start at the very beginning of the nightmare scenario you're already thinking about. If our own sun somehow wandered into the danger zone of a supermassive black hole in that perfect mass range, what would the actual sequence look like, moment by moment? And what would you see, watching from the relative safety of billions of kilometers away? So let's actually do it. Let's throw our own sun past a black hole and watch what happens. Not from right next door, of course. In this thought experiment, Earth and the rest of the solar system are safely parked billions of kilometers away, coasting in the dark like an audience in the cheap seats. Out there in deep space, we place a supermassive black hole with 1 million times the sun's mass. You know the one. The quiet, invisible monster you've seen as a diagram. A black pit in a flat grid. Now we give our sun a doomed orbit that swings it right past that monster. At first, nothing looks too dramatic. From far away, the sun still looks like a round, glowing ball, tracing a graceful curve. But as it falls toward the black hole, gravity stops being gentle and starts picking favorites. The side of the sun closer to the black hole feels a stronger pull than the far side. Because here's what nobody tells you. Spaghettification doesn't wait for the event horizon. The stretching starts as soon as those tidal forces get serious. Cross the tidal radius, and the sun loses the right to be a sphere. It bulges into an egg shape, then an even weirder teardrop, and then, in a matter of hours, the star we grew up with is pulled into a long, thin filament of gas. Imagine the sun drawn out into a glowing noodle, looping around the black hole, potentially thousands of kilometers long, its once orderly layers shredded into a streaming, spiraling river of plasma. From our distant vantage point, the real show is that it isn't the sun's shape, it's the light. As that river of gas whips around, some of it overshoots and escapes. But a huge fraction swings back and collides with itself. The debris circularizes, forming a hot, dense accretion disk. In a few days to a few weeks, that disk flares. For a brief time, the energy pouring out in X-rays and ultraviolet can rival, or even outshine, an entire galaxy. To us, the black hole that was invisible becomes a beacon. Jets may lance out along its poles, thin beams of near-light-speed particles carving into space. The timeline is brutal, but not instantaneous. Hours to days for the initial shredding. Weeks to months for the peak flare as the most tightly bound debris rains back down. Then months to years of a fading tail, a slow cosmic afterglow as the remaining gas trickles into the disk and vanishes across the horizon. By the end, the sun we knew is gone. In its place, a luminous, swirling ring of gas that dimmed, cooled, and was finally swallowed, leaving behind a black hole that's just a little heavier and a lot harder to ignore. And yet something is above the planets. Something is below them. Because now our quiet solar system has a new directional landmark. The place where the sun once was, and the direction of the thing that ate it. So what would that look like on real telescopes? And how close have we already come to watching this exact picture play out for other stars? From Earth's point of view, a star's death by black hole sounds like the kind of thing that should keep you up at night. A sun-sized object getting torn into a glowing noodle, blasting X-rays across space. That feels dangerous. But here's the twist. For us, almost all of these events are fireworks you can only see with a telescope, not with sunscreen. The tidal disruption events we've already caught, like ASN 14 Li or AT219 QIS, are ridiculously bright. For a few months, they can rival the output of an entire galaxy, and yet by the time that light washes across the solar system, the energy is spread over such an enormous sphere that it's barely more than a whisper. You'd get more radiation from a medical X-ray than from a distant star being torn apart billions of kilometers above or below our little orbital plane. Because here's what nobody tells you. Dangerous in space is almost always a distance problem. Double the distance, the intensity drops by a factor of 4. Multiply the distance by 1,000,000, the beam that could fry a nearby planet becomes a gentle flicker on our detectors. So when we talk about these events lighting up the universe, we mean on cosmic maps, not on your skin. Could there be an exception? What if a star was shredded uncomfortably close to home? Now we're in the realm where the details matter. You'd need a black hole within our own galaxy, relatively near our orbit, and you'd probably need it to launch a jet pointed almost straight at us. That's the only configuration where the high-energy radiation could rise above interesting and into concerning. Pattern interrupt. We actually do have a supermassive black hole in the neighborhood. You know the one. Sagittarius A, the 4 million solar mass monster at the center of the Milky Way, about 26,000 light-years away. If a star wandered too close and Sagittarius A had a full tidal disruption event tomorrow, it would be one of the most spectacular things we've ever seen in X-rays and infrared. But harmful? Not from that distance. Its radiation would be diluted long before it reached the solar system. For us, the worst side effect would be clogged telescope schedules. So, let's start at the very beginning of our risk calculation. Violent does not automatically mean dangerous to you. These are safe explosions, safe spaghettifications. We get to watch gravity do its most extreme tricks while sitting in a quiet suburb of the galaxy. And that's the real impact. Not on our bodies, but on our picture of how black holes grow, how galaxies feed, how the cosmic web recycles stars into new generations. Because once you realize we can watch these deaths from a safe distance, the next question isn't, are we okay? It's, What can we learn from the way a black hole eats? So if watching a black hole eat a star rewires our picture, the next question is brutally simple. How much does the beast actually grow? Does one unlucky sun really matter to something that already outweighs millions of suns? Now let's begin with a single meal. Take a star like our sun. During a tidal disruption event, it's shredded, stretched into a glowing stream, and flung around the black hole. But here's the twist. Only about half of that stellar mass usually ends up falling in. The rest is hurled back into space as high-speed debris. Because here's what nobody tells you. Even when a black hole wins, it wastes a lot of food. Put that in perspective. A typical supermassive black hole in a big galaxy might be tens million times the mass of the sun. Swallow half a sun, and you've increased its mass by about 1 part in 20 million. That's like adding a grain of sand to a mountain. Technically true growth. Emotionally underwhelming. And yet something is above the planets. Something is below them. In the same way, something important hides above and below that tiny fraction. Because a galaxy doesn't get just one tidal disruption in its lifetime. Over cosmic time, it gets thousands, maybe tens of thousands. Tidal disruption rates are estimated at about one event every 10,000 to 100,000 years per galaxy. Rare on human timescales, yes. But over 10 billion years? That's a steady, if slightly gruesome, drip feed. In a giant galaxy with a billion solar mass black hole, this drip is just garnish on an already massive meal, mostly built from gas inflows and galaxy mergers. But in smaller galaxies, with black holes only a few 100,000 solar masses. Each disrupted star is a non-trivial percentage change. Stack up thousands of those, and you're no longer talking about rounding errors. You're talking about a real chapter in the black hole's growth history. And the impact isn't just in mass. When a black hole feeds, it lights up. A single tidal disruption can release as much energy in a few months as our sun will emit over its entire 10 billion year lifetime. That energy doesn't just vanish into space. It slams into the surrounding gas, heating it, pushing it, sometimes blowing it out of the galactic center entirely. So, let's start at the very beginning of a feedback loop. The black hole eats, the flare heats, and expels gas. That missing gas can't form new stars, and it can't easily fall back in to feed the black hole again. This is how you end up with a kind of cosmic thermostat. Too much feeding. The outburst chokes off the supply. Too little. Gas cools, drifts back in, and the next star wanders too close. By watching tidal disruptions in many galaxies at different distances, we're effectively watching this thermostat at different settings, across billions of years. You know the one question that follows. If these events are so important, how do we actually catch them in the act, given they're so rare for any one galaxy? That's where the real observational tricks begin. Because here's what nobody tells you. A black hole eating a star sounds like one single, dramatic thing. One picture in your head. But when we actually watch these tidal disruption events light up the sky, they come in wildly different flavors, like a cosmic tasting menu of destruction. Some flares blaze for days, others smolder for years. Some are blindingly bright in X-rays, others barely whisper in the optical and ultraviolet. Why? It's not just one dial, it's a whole control panel. Star type, black hole mass, the exact orbit, even where you're sitting in space when you watch the show. All of that shapes what you see. So, let's start at the very beginning. What kind of star is being torn apart? Shred a puffy red giant and you get a very different signature than from a dense main sequence star like our Sun. Giants are huge, low-density clouds of gas, so gravity can start peeling them apart gently over a wider region. The flare can be slower, softer, spread out in time as the debris trickles back. Main sequence stars are more compact. When they cross that tidal radius, the encounter is sharper and the flare can rise and fall more quickly. Then there are white dwarfs, tiny, incredibly dense. If one of those wanders too close to an intermediate mass black hole, the tidal squeeze can actually ignite thermonuclear reactions in the star's core. You don't just get a flare from falling gas, you get a kind of one-time forced supernova, layered on top of the feeding frenzy. It's like the black hole both crushes and lights the match. Now add black hole mass to the mix. For smaller supermassive black holes, the tidal radius sits safely outside the event horizon, so the star is shredded where we can see it. For the really big monsters, the shredding zone can drop inside the horizon. The star still dies, but from our point of view, it just vanishes. No bright flare, no dramatic light curve, just silence. And yet something is above the planets. Something is below them. In the same way, your viewing angle in these events defines your whole picture. Look face on at the new accretion disk, and you might see a smooth optical, white UV glow. Look edge on and dust or outflowing gas can block the inner regions, so you get a dimmer, redder flare. If a relativistic jet happens to be pointed almost right at you, the beamed X-rays and gamma rays can outshine the entire host galaxy, turning a quiet disruption into a spectacular jetting TDE. Some events roar in X-rays as the innermost orbits heat to tens of millions of degrees. Others are dominated by optical and ultraviolet light from the outer debris and reprocessing clouds. Some light up the radio sky as fast outflows slam into the surrounding gas, like a miniature supernova remnant forming in real time. Now let's begin to reframe that simple phrase. A black hole eats a star isn't a single phenomenon. It's a whole family of related catastrophes, tuned by mass, structure, and geometry. Which raises the next problem. With so many flavors, how do we even know what we're looking at when a new flare appears? So here's the uncomfortable twist. With all those different flavors of star death flares, we're almost certainly only seeing the loudest, showiest ones, the cosmic drama queens. Because our telescopes, they're biased. Most of the tidal disruption events we've cataloged come from surveys that stare at the sky in optical and ultraviolet light, looking for bright, months-long flares that stand out against a galaxy's glow. That means if a black hole's meal is faint, short, or peaks in a different part of the spectrum, it slips right past us. It's like judging the whole solar system from a single flat picture and assuming nothing interesting happens above or below the plane. Because here's what nobody tells you. Galactic centers are messy. They're packed with dust and gas, swirling like a thick cloud around the central black hole. That material is fantastic at absorbing optical and UV light, the exact wavelengths many surveys depend on. So a star can be shredded, heated to tens of thousands of degrees, blast out a brilliant flare. And from our vantage point, the dust just shrugs and turns it into a gentle infrared glow or a buried X-ray whisper. We only catch those hidden meals when we're lucky enough to be looking with the right eyes, space telescopes and X-rays, or infrared surveys that can see through the smog. How many flares are going off right now behind those dusty curtains in galaxies we think are quiet? How many black holes are secretly on a high-calorie diet, And then there are the truly stealthy predators. For very massive black holes, the tidal radius where a star would be torn apart sits inside the event horizon. The star crosses the point of no return before gravity can rip it into a visible stream. From the outside, there's no bright flare, no long decay, just a slight uptick in mass hidden behind the horizon. A whole star disappears, and space barely raises an eyebrow. So if bright, long-lived TDEs are the textbook examples, what about the weird ones? We're starting to see fast transients that flare and fade in days, or odd X-ray bursts that don't match the classic months-long decline curve. Some look like partial disruptions, where a star only loses its outer layers and then limps away on a new orbit, ready for another close pass. You know the one, the horror movie sequel where the monster wasn't actually dead. Now let's begin to think bigger. If all we've mapped so far is the tip of the iceberg, what would a truly complete census of star-eating events reveal about the hidden lives of black holes, and what else they might be quietly reshaping in their orbits of influence? So here's the twist. Those big months-long tidal disruption events we've been talking about. They're the slow, cinematic version. Out in deep space, there's a whole zoo of much faster, weirder flashes that pop on and off before you've even finished refreshing the telescope dashboard. Astronomers call them transients. Fast blue optical transients that flare and fade in a night or two. X-ray bursts that scream for seconds, then drop back to silence. Radio blips that show up once and never repeat. It's like the sky is full of cosmic jump scares, and we're still trying to label the monsters. Because here's what nobody tells you. The universe is not a calm, flat picture. It's more like a strobe light. Now, let's begin to connect this chaos back to star-eating black holes. Some of these fast blue optical transients are suspiciously hot and bright, as if a huge amount of energy was dumped into a very small region of space in a very short time. You look at the spectra, you look at the color, and something feels off if you try to call it a normal supernova. So a growing camp of researchers has asked a provocative question. What if these are tidal disruptions too, just with oddball parameters or a strange viewing angle? Picture a star in a plunging orbit that only gets partially shredded, or a black hole that launches a narrow jet straight past our line of sight. You might not see the classic smooth months-long flare. You might see a sharp blue spike as the debris slams into itself, or a brief X-ray flash as the jet whips around, then nothing. From our vantage point, it's like catching one frame of a movie and trying to guess the whole plot. And that's the real challenge. Most of these events are discovered by wide-field surveys that scan huge swaths of sky, but only every few nights. By the time we notice a weird light curve and swing the big telescopes over for follow-up, the main act is often already over. The data are noisy, the rise and fall are poorly sampled, and you're left arguing in front of a whiteboard about whether your single jagged bump matches a black hole snack, a failed supernova, or something we don't even have a name for yet. So let's start at the very beginning of the next revolution. Within the next few years, the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will start imaging the entire visible sky every few nights with ridiculous sensitivity. Instead of a handful of fast, mysterious flashes, we'll see thousands. We catch more of them in the act, with cleaner light curves, earlier triggers, and rapid follow-up across X-ray, optical, and radio. And yet something is above the planets. Something is below them. In the same way, above and below the tidy textbook picture of a slow tidal disruption, there's a whole layered reality of rare, extreme star-black hole encounters. Stars skimming the tidal radius. Stars on eccentric orbits. Stars swallowed, almost whole. As we fill in that three-dimensional landscape of transience, the story of what really happens when a black hole swallows a star is still being written. The next bizarre flash we catch could be the first clear glimpse of a kind of stellar death we've only imagined on paper. So the question you're left with is simple. If we're only now learning to see these quick, violent meals, what even stranger appetites are we about to uncover? So if those quick, violent meals are only just coming into focus, we have to zoom out and ask a bigger question. Where do these star-eating moments fit in the life of a galaxy? Because here's what nobody tells you. A single tidal disruption isn't just a local tragedy for one unlucky star. It's a line item in the energy budget of an entire galactic center. Every time a black hole shreds a star, about half the debris is flung back into space, and the other half spirals inward. That infalling cloud doesn't just disappear. It releases as much energy in a few months as a normal star like our Sun will emit over its whole 10 billion year life. That flare of X-rays, ultraviolet, and sometimes jets is feedback. It heats and stirs the gas near the core, pushes on surrounding clouds, and ever so slightly fattens the black hole itself. Now let's begin to compare that with the more familiar picture. You know the one. The blazing quasar powered by a supermassive black hole gorging on a steady river of gas. In those active galaxies, the black hole is in buffet mode, swallowing a continuous inflow from the disk of the galaxy. The accretion disk is long-lived. The output is more or less sustained, and the whole thing can dominate the light of the host galaxy for millions of years. Tidal disruptions are the opposite vibe. They're sporadic. They're messy. Instead of a calm, flat feeding disk, you get a star in a wild orbit that plunges too close, is torn into a thin stream, and briefly turns the black hole into a lighthouse. Then the flare fades, the orbiting debris settles or escapes, and the giant goes dark again. In terms of mass growth, these events are snacks compared to the meals that power quasars, but they're spectacularly efficient at converting mass into light. And here's where it gets really useful for us. Most galaxies in the nearby universe are quiet. Their central black holes aren't running bright accretion disks. They're dormant, invisible against the glare of their stars. In those systems, a tidal disruption event might be the only time the central black hole announces, "I'm here." For a few months, the core of an otherwise ordinary galaxy spikes in brightness, and we catch a black hole that would never show up on a normal survey. Because once you start counting those flashes across many galaxies, spirals, ellipticals, compact dwarfs, you're doing more than collecting fireworks. You're probing how stars orbit in the crowded central regions, how often gravity nudges them onto death-plunge trajectories, and how many black holes of different masses are actually out there. The observed rate of these events feeds directly into our models of stellar dynamics and black hole demographics, telling us whether our picture of galactic centers is even remotely right. So, in a universe where most stars are born in calm clouds, shine for billions of years, and die as white dwarfs or supernovae, what does it mean that some end as fuel for the darkest objects we know? Is that just a statistical footnote? Or is it a clue that black holes are quietly shaping the evolution of galaxies far more than our current picture admits? Hold that thought, because to answer it, we have to follow one star all the way in, from its safe orbit to its final stretched out scream, at the edge of the event horizon. So let's go back to the picture in your head, the one we all start with. It'd be a flat funnel in space, a little marble star rolling around the rim, then spiraling down a drain into darkness. Clean, simple, one motion, one moment. Because here's what nobody tells you. That diagram is a story choice, not a photograph of reality. We drew it that way. We decided to emphasize the event horizon, to make the black hole look like the bottom of a cosmic sink, and to quietly erase everything messy that happens before a star ever gets close enough to cross that invisible edge. By now, you've seen how wrong that simplicity is. In the real sequence, the star doesn't just fall in. First, its orbit is nudged, twisted by the gravity of other stars, maybe by a passing cloud of gas, maybe by a disrupted binary partner. It can loop around the black hole for ages, deflected and redirected, long before anything dramatic happens. That whole dance is missing from the funnel. Then there's the tidal radius, the one we've been hinting at. The distance where the black hole's gravity across the star is so uneven that the star is stretched into a noodle and torn apart. That radius can sit well outside the event horizon, which means the shredding, the flare, the bright tidal disruption event we actually observe all happen in a region the classic diagram barely acknowledges. Every sketch you've ever seen is choosing sides. Do we draw the smooth, heroic plunge across the horizon? Or do we draw the chaotic stream of gas, whipping around in orbit, colliding with itself, circularizing into a hot disk that lights up in X-rays and launches jets? We usually can't draw both without confusing the eye, so we pick one. And the choice quietly rewires your intuition. Even our language does it. We say the black hole eats the star, or that the star is swallowed. Sounds like a single chomp, right? One bite, done. But what we've actually described is a months-long, sometimes years-long sequence. First orbital deflection, then stretching, then disruption, then a flare as debris rains back in, then a glowing accretion disk, then jets. And only then does some fraction of that gas finally slip through the horizon. The meal is a whole movie, not a single frame. So, let's start at the very beginning the next time your brain reaches for that flat funnel. Pause it. Mentally replace the marble, rolling inward with a time lapse. A star wandering in from the wider galaxy, its orbit twisted, its body pulled into a stream, half its mass flung back into space, half captured and spun into a disk that briefly outshines its entire host galaxy. Does that change how you feel about the phrase, fell in? This isn't just semantics. When you watch real data from a tidal disruption event fade over months, your mental model decides what you think you're seeing. A single gulp, or a black hole star encounter stretched across time and space. In the next section, we're going to take that richer movie and line it up, frame by frame, with the actual light curves and spectra astronomers record, so you can read those signals with the right picture in mind. So let's turn that idea of a single cosmic gulp into what it actually is, a sequence of scenes, a whole movie playing out around a black hole. Because here's what nobody tells you. When a black hole eats a star, the real action happens long before anything touches the event horizon. So, let's start at the very beginning. Picture a star in your mental galaxy, just minding its orbit around the center. Then something nudges it. Maybe it's a close pass with another star, maybe a disrupted binary system. But the orbit is perturbed just enough that this star is now on a long, plunging path toward the black hole. In your movie, this is the wide shot. a tiny point of light starting to fall inward under relentless gravity. Next scene, the approach to the tidal radius. That's the invisible boundary where the black hole's gravity across the star's diameter is stronger than the star's own self-gravity. At first, the star looks normal. Then, as it crosses that radius, you give it a subtle visual twist. The near side of the star is pulled harder than the far side, so the sphere becomes a slightly distorted teardrop, stretched along its orbit. Keep the camera closer now. As it dives deeper, the stretching ramps up. The star turns from a teardrop into a glowing noodle, a filament of gas being drawn out like molten taffy. This is the onset of full disruption, where the star stops being a single object and becomes a continuous stream. You know the one, the classic spaghettification scene, but extended in time, not just one dramatic frame. Then the star is gone as a star, but not gone from the story. Half of that noodle is flung out into space, the other half loops back. Imagine a long, arcing stream of gas swinging around the black hole, overshooting, then colliding with itself as different parts of the orbit intersect. Those collisions rob the gas of energy and angular momentum, forcing it to settle. That settling gives you the next visual anchor, a thick, glowing disk. The debris circularizes into an accretion disk that heats to millions of degrees, lighting up in X-rays and ultraviolet. On top of that disk, in some events, you can sketch narrow-focused jets punching out of the galaxy's plane like twin searchlights in deep space. The flare is the bright middle of the movie, the disk blazing, the jets roaring, the star's death scream in light. Then slowly, the luminosity fades as the accretion rate drops, and the black hole quietly feeds on the remaining gas. The event horizon is the final, silent shot, where the last wisps slip through and vanish from our view. Now test this picture. The next time you see a black hole in a movie or article, ask, which scenes are they showing you, and which parts of the real tidal disruption movie are missing? So that whole movie we just watched, the clean arc from first stretch to final fade, that's our best current picture of a tidal disruption. But it's not the whole story, not even close. Because here's what nobody tells you. The biggest mysteries in this field are hiding in the parts we just hand-waved past. For example, those spectacular jets we sometimes see shooting out at nearly the speed of light when a star is torn up. We know they're powered by gravity and magnetic fields. But what exactly flips the switch? Is it the spin of the black hole, the thickness of the debris disk, the tangled magnetic cloud the star brings in, or something we haven't even modeled yet? Even the shredded star itself is still a puzzle. In simulations, the debris forms a long, thin stream that whips around the black hole and crashes into itself. But in 3 dimensions, that stream can twist, fragment, and break into clumps. How smooth is it really? Does it stay like a cosmic noodle, or does gravity turn it into a messy spray of orbiting droplets? You know the one, the simple diagram that shows a neat ribbon spiraling in. Real debris probably laughs at that flat, tidy picture. We're also not sure how often the star actually dies. Sometimes we think the black hole just takes a bite, peels off the outer layers, and the core slingshots away, scarred but still orbiting the galaxy. Other times, the whole star is erased. What fraction are partial disruptions versus full disintegrations? Right now, we only have a small sample, and the universe isn't exactly labeling its casualties for us. And the rates themselves? Huge question mark. Our telescopes only see parts of the sky in limited colors for limited times. A flare that's bright in X-rays but faint in visible light might be missed by one survey and caught by another. Dust can hide events in the plane of a galaxy the way a thick cloud hides the sun. So our estimates of how often black holes eat stars are still rough. Future all-sky surveys that scan the whole celestial plane over and over will help, but we're not there yet. On the theory side, the challenge is brutal. To really model a disruption, you need full 3D magnetohydrodynamics. Gravity, gas, radiation, magnetic fields, and a star with a realistic internal structure all evolving at once. Each simulation is like building a miniature universe inside a supercomputer. Even then, we're mostly probing the external, classical side of the black hole. The information paradox, the question of what happens to the star's quantum information once it crosses the horizon, remains untouched by these events. The tidal flare is outside. The real argument is happening at the edge of the event horizon, where our equations start to disagree. So we're watching this in real time. New events, new simulations, new surprises. This isn't a finished chapter in astrophysics. It's an active frontier. Now, let's begin the really wild part. What happens when we stop just watching these events and start using them as tools to map the invisible hearts of galaxies? So here's the next question. Could we ever know a star is doomed long before the black hole takes its final bite? Not just a flare popped up in some distant galaxy, but that one, right there, will be shredded on this date, in this orbit. Because here's what nobody tells you. In principle, the danger is written into the orbits already. Every star near a galactic center is moving through a tangled gravitational minefield, nudged by other stars, by clouds of gas, by the central black hole itself. If we could map those orbits with absurd precision, we wouldn't just see a chaotic swarm. We'd see which paths skim the tidal disruption radius, which systems are one close encounter away from being thrown onto a death plunge. Now, let's begin with the part that sounds almost reasonable. We already track stars around the black hole at the center of the Milky Way. You've seen the time lapse. Little points of light whipping around an invisible mass, completing orbits in just a few decades. Scale that up. Imagine a future observatory that can do this not for a dozen stars, but for tens of thousands across many galaxies, watching their orbits precess and wobble in 3 dimensions. At that point, predicting a tidal disruption event becomes less prophecy and more long-term weather forecast. And then we push it further. What if we don't just know which star is doomed, but actually watch the approach in real time? With ultra-precise astrometry and long baseline interferometry, we could trace the star's path as it skims closer and closer, see its image stretch and shear as gravity starts to pull harder on the near side than the far side. To your eyes, it would still look like a point. To a future array spanning half the solar system, it might look like a teardrop, then a noodle, then a torn ribbon of gas. Pattern interrupt. We usually think of black holes as silent. But in this future, the death spiral would be anything but quiet. Next-generation X-ray observatories could watch the hot inner regions of the debris disk flicker as clumps of stellar material fall in, each flare tracing the last few orbits. Gravitational wave detectors tuned to higher frequencies than we have now might pick up tiny ripples from the star's distorted core as it's pulled apart, letting us hear the disruptions in space-time itself. None of this breaks physics. It just stretches our instruments. So, let's start at the very beginning of that technology curve. Better mirrors, longer baselines, more sensitive detectors. The same techniques we're using now to image black hole shadows and track nearby stars are the seeds of this predictive era. And yet something is above the planets. Something is below them. Our own solar system is already a test bed for building the kind of precise, three-dimensional maps we'd need. So picture this. You're alive in a time when astronomers can point to a star in some distant galaxy and say, in 50 years, that one dies. You watch its orbit tighten over decades. You watch the final plunge over months. You know the exact moment when gravity wins. What new secrets about black holes would we unlock if we could plan, in advance, to witness a star's last heartbeat? And that brings us to an even stranger thought. Once you can predict a death like that, can you use it? To weigh, to test, to probe the black hole itself in ways we haven't even tried yet? So let's start at the very beginning, before the last heartbeat, before the countdown. Picture a perfectly ordinary star, just minding its business in the crowded center of a galaxy. It's been there for billions of years, tracing a quiet orbit through a maze of other stars, gas and dust, all wrapped in the invisible pull of a supermassive black hole. Nothing looks dramatic at first. The star just circles, the way planets in our solar system circle the sun in a flat plane. But because here's what nobody tells you, that calm orbit is balanced on a knife edge of gravity. Other stars drift by, a passing cluster tugs just a little too long, or a binary partner gets nudged. One tiny change, and the star's path bends inward. Now the camera cuts in closer. Each loop brings it nearer to the black hole. From far away, the star looks the same, bright, round, safe. But as it crosses the critical radius, the tidal radius, the symmetry breaks. On the side facing the black hole, gravity pulls harder. On the far side, weaker. The star feels a stretch. Just a hint at first, like a slow-motion tide. Then we push the slider forward. That subtle stretch becomes spaghettification. The star elongates into a glowing noodle, thousands of kilometers long. Its near side races ahead, its far side lags behind, and the whole thing is torn into a thin, luminous stream. Half of that stream is flung back into space. The other half curves around, captured. From above you see the stream wrap once, twice, colliding with itself, circularizing. The debris flattens into a hot, whirling disk around the black hole, like a deranged, supercharged version of the protoplanetary disk that once formed our own planets. Friction and gravity heat it until it blazes in X-rays and ultraviolet. In some cases, twin jets lance out along the black hole's spin axis, punching into interstellar space at nearly light speed. Cut to us. Telescopes scan the sky, and suddenly, there it is, a new point of light where there was only darkness. It brightens over days, peaks, then fades over months, releasing in that brief flare as much energy as our sun will in its entire lifetime. We take spectra, watch the color shift, track the change in lines as debris falls back in. From that flicker, we decode the mass of the black hole, the geometry of the disk, even how fast space itself is being dragged around it. For the star, this is a violent execution. For the black hole, it's a snack, a tiny growth spurt. For us, it's a message, a burst of information about extreme gravity that lets us test the very picture of what a black hole is. And yet something is above the planets. Something is below them. In the same way, there's what we draw, and then there's what actually happens. So as we zoom out from this one doomed star, how should we really imagine all the other deaths and all the other black holes waiting in the dark? So the first thing to throw out is that old cartoon in your head. The one where a star just drifts too close, touches a black circle, and blinks out like someone hit delete. You know the one. After everything we've walked through, does that picture even feel usable anymore? Because here's what nobody tells you. Once you zoom in on a real tidal disruption, a black hole isn't a quiet drain in space. It's a whole sequence. A star wandering in from some tilted orbit, the gravity gradient rising, the outer layers stretching into a noodle, the core lagging behind, the whole thing whipped into a long, glowing stream that can outshine an entire galaxy for a moment. That's not a single event. That's a story. And that story doesn't end at the event horizon. It feeds back into the galaxy around it. When half that shredded star falls in and half is flung back out, you're not just losing a star, you're stirring the central region with new gas, shock waves, and sometimes relativistic jets that punch through the galactic plane. Black holes stop looking like endpoints and start looking like engines, quietly retuning their environments over millions of years. So now, when you imagine a galaxy, you don't just see a flat spiral of stars in orbit like a tidy solar system diagram. You see a thick, dynamic ecosystem with a central black hole trading mass and energy with its neighborhood. Tidal disruptions are just the most dramatic episodes in that exchange, like sudden storms in a long, slow climate. This is why these events matter so much more than a cool visual. When we watch a tidal disruption fade over months, we're watching gravity convert ordered motion into light, heat, and jets in real time. We're testing how energy flows when the rules of general relativity take over. We're learning how stars live, die, and sometimes get recycled into the next generation of clouds and orbits. Now let's begin to use that as a new mental model. A black hole is not a mysterious void that breaks physics. It's an extreme laboratory where the same rules we use for falling apples and satellite orbits are pushed to terrifying limits. The equations don't stop working there. They get loud, and every tidal disruption event we catch is like another experiment we didn't have to build. And yet something is above the planets. Something is below them. In the same way, there's what your intuition draws. And then there's the layered, three-dimensional reality hiding behind the flat picture. This upgraded view of black holes is just one example of how the universe keeps forcing us to trade simple icons for richer, stranger stories. So what other familiar cosmic images are overdue for an upgrade? In the final stretch, let's pull back even farther and see how this one violent encounter fits into the larger map of the cosmos you carry in your head. We started this journey with a flat sketch, a black circle, a star, a simple arrow from before to after, clean, painless, almost polite. But by the time we followed that star all the way in, that neat little icon had exploded into a three-dimensional, time-evolving nightmare of torn gas, spiraling orbits, and delayed flashes of light. So what changed? The black hole didn't. The star didn't. We changed the picture. We stopped pretending that one frozen diagram could capture a process where gravity keeps rewriting the script every millisecond. Because here's what nobody tells you. The more violent the universe gets, the more dangerous those flat single-frame diagrams become for your intuition. We need them, of course. You can't think about a tidal disruption event if all you have is a chaotic, movie-length simulation in your head. So, let's start at the very beginning of how we think. We draw a line, a plane, a little cartoon orbit, and we say, here, this is the idea. Simple models are like training wheels for the mind. Without them, you never get moving. But if you never let go of them, you never really ride. A flat sketch of a star crossing an invisible boundary makes it look like the story is about a single moment. Cross the line, vanish, the end. In reality, that moment is stretched into months or years of drama. The star is shredded into a long, looping stream. Half of it is flung back into space. The other half rains down and bursts, lighting up the region around the black hole over and over. Where exactly is the after in that? This is the tension we keep running into in space science. We crave the before and after. Stable star, quiet black hole. Then, boom, new equilibrium. But the universe keeps hiding the real story in the messy in between. Galaxy formation isn't a single collapse. It's billions of years of mergers, feedback, and wandering clouds. The Big Bang isn't just a point in time. It's an ongoing expansion with relic radiation, dark matter, and structure still unfolding. And yet something is above the planets. Something is below them. We love to slice cosmic history into tidy layers. So here's the rule of thumb. Be suspicious of any cosmic story that jumps from once there was to and now there is without showing you the middle. If a black hole eats a star and all you see is two flat panels labeled before and after, what crucial fireworks are missing between those frames? What would change in your understanding if you insisted on seeing the whole orbit, the whole flare, the whole cascade of cause and effect? That's the gap we try to live in on this channel. The diagrams are the doorway, not the destination. Because once you start demanding those rich, three-dimensional, time-soaked stories, the entire universe shifts from a poster on your wall into a living, violent environment you can almost step into. And in the next part, we're going to push that even further by asking what other comforting cosmic pictures might fall apart the moment you press play instead of pause. So now, when someone says, a black hole just eats a star and it disappears, you can feel it. That tiny itch in the back of your mind that says, not quite. Because here's what nobody tells you. You're walking around now with a full three-dimensional movie in your head, not a flat headline. You can see the star wandering in from the crowded core of a galaxy, or falling out of a broken binary. You can feel the gravity rising as it crosses that invisible tidal radius, where the gentle pull becomes a cosmic torture rack. You know the one. The moment where the star doesn't just fall in, it's shredded. Spaghettified into a glowing stream, half of it flung back into space, half of it whipped around to build that furious, swirling disk. When you hear the black hole swallowed it, you now picture X-ray flares, ultraviolet screams, maybe even jets punching up and down out of the plane like cosmic blowtorches. That is a new sense you didn't have an hour ago, a kind of astrophysical X-ray vision. You can look at a simple diagram or a one-line tweet and mentally press play. You see the orbits, the debris, the time evolution. And yet something is above the planets. Something is below them. In the same way, something is hidden above and below every flat picture of a black hole feeding. So here's the small favor. Next time you see a black hole drawn as a 2D funnel with a little cartoon star dropping in, pause for half a second. Can you quietly upgrade it in your mind? Can you be the person in the room who says, actually, that star would light up the galaxy for months before most of it ever crossed the horizon? You don't have to be annoying about it. Just an ambassador for the full version. Because once a few more people start demanding that full version, we get to tell bigger, wilder stories. If you value this kind of slow, cinematic walk through a violent event in space, Subscribing or sharing is the simplest way to vote for more of it. One click from you tells the algorithm, yes, this. More of this, less of the flat poster. And we're not stopping at one doomed star. Now let's begin to widen the menu. Next episodes, we're diving into neutron star mergers that ring space-time like a bell. The tangled birth of the first galaxies out of a collapsing cloud of dark matter. Even what the interior of a black hole might look like, if we follow the equations all the way in, you'll get the same step-by-step, no magic skips treatment there too. So thank you for spending this time tracking one star from ordinary orbit to extraordinary ending. Of all the ways you could have used these minutes, you chose to fall into a black hole with us. That's a choice we don't take lightly. So before you go back to notifications and to-do lists and the very non-relativistic pace of normal life, hold on to one last picture. We started with a paradox. The darkest objects in the universe announcing their meals with some of the brightest lights we can see. In space, there is no up, there is no down. And yet something is above the planets. Something is below them. In the same way, black holes are supposed to be the ultimate hiding places. And yet when a star wanders too close, they light up like a cosmic flare gun that can outshine an entire galaxy. Because here's what nobody tells you. While you're watching this, that drama is unfolding all over the universe. Right now, in the crowded cores of distant galaxies, stars are drifting through gravitational minefields, nudged by neighbors, kicked by passing clouds of gas, slowly deflected into deadly orbits around their central black holes. Most of those tidal disruptions will never get a name. They'll just be one more brief brightening in a survey telescope's data. A star's final scream, written as a fading spike of X-rays. So the next time you step outside and look up at what feels like a calm, quiet sky, remember what that calm really is. Every point of light is a story in progress. Some of those stars will burn peacefully for billions of years. Some will explode as supernovae. And some, far in the deep future, will wander just a little too close to the dark centers of their galaxies and be pulled apart, atom by atom, by tides that make our ocean tides look like a gentle shrug. You know the one, the flat picture of a spiral galaxy with a neat, bright core and tidy arms. Now tilt it in your mind, fly into that core and imagine the brightness they're breathing. A slow, dangerous heartbeat, each pulse a star being shredded, half of its mass flung back into space, half spiraling down, heating into a disk so hot it radiates across the universe before vanishing past the horizon. So, let's start at the very beginning of your next night walk. When you glance up, what will you see differently? Will you think of those invisible orbits around black holes, of light that is literally the byproduct of destruction, in a universe where even being torn apart becomes a source of illumination? What other hidden stories are waiting in the spaces between our simple diagrams and the reality they're trying to flatten? If you want to keep unfolding those stories with us, you know where to find them. As we fade out, picture the center of a galaxy on your screen, slowly brightening, slowly dimming, as one star after another crosses the line between ordinary orbit and extraordinary ending, and then, quietly, disappears. So here's the unsettling part. That quiet galaxy center you're picturing, it's rolling the dice on star-eating events all the time, just very, very slowly. On average, we think a typical galaxy with a central black hole shreds a star about once every 10,000 to 100,000 years. That sounds almost comically rare. You could live your whole life, your civilization could rise and fall, your solar system could complete dozens of orbits around the galaxy, and never see your own central black hole light up this way. Because here's what nobody tells you. Rare in one galaxy does not mean rare in the universe. So, let's start at the very beginning of this little cosmic accounting trick. Astronomers estimate there are on the order of 100 billion galaxies in the observable universe. Take that slow rate, say one tidal disruption every 50,000 years per galaxy, and multiply. You get roughly 2 million stars being torn apart per year across the observable cosmos. Break that down and you're at a few dozen tidal disruption events per day. Right now. As you watch this, somewhere in space, a star is crossing the line and being unspooled into a glowing, falling cloud. How does that compare to more familiar fireworks, like supernovae? Core collapse supernova in a big galaxy might go off once every 100 years or so, and type Ia add a few more over longer timescales. So per galaxy, supernovae outnumber tidal disruptions by maybe a factor of 100 or more. In a single galaxy, black holes are the quiet predators, exploding stars are the loud neighbors. But zoom back out to the full picture and the numbers start to rhyme. Across all galaxies, we're talking a few supernovae per second, and a tidal disruption every few seconds to minutes. Not equal, but not negligible. The universe is running both shows at once. Stars blowing themselves apart, and stars being taken apart. And yet, something is above the planets. Something is below them. In the same way, something is above our simple counts, and something is below. Detection bias. We only see the brightest, best-timed flares in galaxies where our telescopes happen to be looking. So astrophysicists play a kind of statistical hide-and-seek. They take the handful of well-observed events, correct for how many they must have missed because the flare was too faint, too short, too dust-obscured, or sitting behind the glare of a busy galactic center, and then scale up. Pattern interrupt. For every tidal disruption we've actually caught, there could be dozens or hundreds we never noticed. The rates you hear quoted are already de-biased best guesses, wrapped in uncertainty bars. But the implication is clear. Even if your home galaxy only sees one of these episodes every tens of thousands of years, the sheer number of galaxies means the universe is constantly alive with these short, violent flares. Black holes and stars are in an ongoing, if infrequent, deadly dialogue, quietly rewriting orbits and growth histories in the background while we draw our flat diagrams and pretend space is simple. Now let's begin the strangest part. What it actually looks like, moment by moment, when a star loses that cosmic argument. Now let's begin that strangest part with a twist you probably weren't expecting. When a star dies in a black hole's grip, it doesn't just light up the universe, it also shakes it. Because here's what nobody tells you. That long, doomed final orbit, where the star is being stretched into a glowing noodle of gas, should also rattle space-time itself. Not as violently as two black holes colliding, sure, but in principle, every change in how mass moves, every lopsided swirl of gravity in that last stretch, sends out ripples. Tiny gravitational waves, racing across space. You've heard of the big ones. LIGO and Virgo listening to the universe, catching those sharp, chirping signals when black holes or neutron stars merge. Those detectors are tuned like very picky radios. They're most sensitive to quick, high-frequency wiggles in space-time from compact objects whipping around each other at half the speed of light. A star being torn apart, that's messier, slower, more like a long groan than a clean musical note. So the signal we expect from a tidal disruption event is weaker, stretched out in time, and humming at different frequencies than the classic merger chirp. That makes it incredibly hard to detect with our current ground-based technology. The Earth vibrates, the mirrors shake, trucks drive by. All of that noise drowns out the subtle, low-frequency waves from a star's final orbit. It's like trying to hear a distant whisper during a rock concert. But fast forward a few decades. Imagine a detector not stuck on a noisy planet, but floating in quiet, interplanetary space. That's the idea behind missions like LISA, the Laser Interferometer Space Antenna. 3 spacecraft in a giant triangle, millions of kilometers apart, following the sun in a smooth orbit. Instead of listening for short, sharp notes, LISA will be tuned to slow, deep bass lines in space-time. Those are exactly the kinds of frequencies you get when a normal star dances its last dance around a massive black hole in a galactic center. In theory, LISA could track the gradual in-spiral, the moment the star crosses the tidal radius, even the changing rhythm as it's shredded into a stream of gas. We'd get a timeline of the death, not just a snapshot. And here's where it gets wild. We're already watching tidal disruption events in light. X-ray flares, ultraviolet flashes, radio jets. If we could pair that electromagnetic picture with a gravitational wave recording of the same event, we'd have a true multi-messenger view. You'd see the flare brighten while you literally measure the changing pull of gravity as the debris falls back in. In that next era of black hole astrophysics, we wouldn't just see a star's death. We'd feel the ripples it leaves behind and use them to map gravity in its most extreme form. And yet, something is above the planets. Something is below them. To really understand how these deaths echo through a galaxy, we have to zoom out and look at where these black holes sit in the larger cosmic landscape. So once you zoom out and see where these black holes live in a galaxy, you can ask a sharper question. What else can they eat? We've been talking about normal stars like the sun, but the universe has a whole menu of compact, weird leftovers. Because here's what nobody tells you. If you feed a black hole the right kind of corpse, you don't just get a flare, you can get a bomb. Take a white dwarf. It's what our sun will become. Earth-sized, sun mass. A dense ember where gravity is already crushing matter into a kind of atomic brick. Now let's begin with a problem. A supermassive black hole would just gulp that white dwarf hole below the event horizon. No drama. But an intermediate mass black hole, something in the middle, say 10,000 to 100,000 suns. That one can tear a white dwarf apart outside the horizon. That's the sweet spot. The tides are strong enough to rip, but not so strong that everything disappears silently. As the white dwarf swings past, gravity can squeeze and stretch it so violently that its carbon and oxygen ignite in a runaway thermonuclear explosion. It's like triggering a type Ia supernova, but with a black hole playing matchmaker. To you, watching from across the universe, this wouldn't look like a standard tidal disruption. The flare would be brief and vicious, rising and fading in days to weeks instead of months. The spectrum would be strange. Some signatures of hot, expanding supernova debris, some from gas spiraling into an accretion disk, maybe even high-energy X-rays from shock-heated material near the black hole. It's a cosmic hybrid, half-star shredding, half-star detonation. Astronomers are hunting these events because they solve 2 mysteries at once. We want to know how white dwarfs die, and we want to know where intermediate mass black holes are hiding. You know the one. That awkward middle child between stellar mass and supermassive that never shows up clearly in our surveys. catch a white dwarf being tidally detonated, and you've basically caught an intermediate mass black hole red-handed. Its mass has to be in that range for the physics to work. And if you think that's extreme, there are even wilder ideas on the table. Could a neutron star be shredded outside the horizon, its nuclear density matter splashed into space? Could exotic objects like hypothetical boson stars or dark matter clumps be torn apart, leaving bizarre, hard-to-interpret flares? The conditions are so intense that our equations start to sweat. We're deep in the regime where quantum physics, relativity, and nuclear reactions all shout at once. So, let's start at the very beginning of the lesson these edge cases are teaching us. The same basic tides that raise an ocean on Earth can unspool a sun, ignite a white dwarf, or pulverize a neutron star. The rules are simple. The outcomes are not. And yet something is above the planets. Something is below them. If these are just the deaths, what does the full life cycle of black holes look like when we follow them across the entire cosmic web? So where does that leave us? When a black hole swallows a star, it doesn't just blink out like a light. It throws a brief, blinding tantrum that lets us watch gravity rewriting the rules in real time. Because here's what nobody tells you. The simple picture is useful, but the real story is gloriously messy. The neat diagram of a star drifting in, crossing a line, and disappearing, you know the one. It hides the tidal stretching, the broken orbits, the spiraling cloud of debris that can outshine an entire galaxy for a few months, then fade back into the dark as if nothing happened. We've talked about stars unspooling into noodles, about half their mass flung back into space and half sinking in, about disks that heat up until they scream in X-rays. That's not an exception to the basic rules of gravity. That is what the basic rules of gravity look like when you push them hard. The rules are simple. The outcomes are not. And that's the pattern you can carry with you every time you look up. Because once you've seen how much drama is hiding in a single star versus black hole encounter, it gets very hard to believe the rest of the universe is simple. Dark matter halos around galaxies, the early universe, a hot quantum foam expanding into something that would one day grow black holes in the first place. These aren't just abstract words in a textbook. They're invitations to ask the same question again and again. If the cartoon is this wild when we zoom in, what is the full resolution picture really doing? Now, let's begin to treat that sense of strangeness as a feature, not a bug. The solar system isn't perfectly flat. Black holes don't perfectly hide what they eat, and our models don't perfectly match what we see. And yet, something is above the planets. Something is below them. Something is always just outside the frame. That gap between the diagram and the data is exactly where discovery lives. So if this changed your mental picture of black holes even a little, don't let it be the last upgrade you give your brain. Tap subscribe, or queue up the next deep dive we've linked for you, and we'll keep peeling back these layers together until impossible starts to feel like Tuesday. What does dark matter really do to the orbits of stars? How did the first black holes light up a universe that was supposed to be dark? As we fade out, hold one last image. A quiet spiral galaxy hanging in space. Its center looks calm, just a dim, dark core. But buried in that darkness is a black hole, and somewhere in its city of stars, one sun is already drifting onto a slow, doomed trajectory. Not tonight, not for millions of years, but one day it will fall, and for a heartbeat, that galaxy will blaze as gravity takes its final bow.